much for the introduction and for hosting me here. So my name is Grigorios Tsagkatakis. Officially, I'm an assistant professor in the computer science department at the University of Crete, and I'm also an affiliate with researchers like Vasilis before me at the Institute of Computer Science at Forth. So the talk is going to be about uncertainty-aware machine learning and some specific cases that we're going to be discussing about for the case of astronomical data analysis. Right, so, I mean, just to give you a really quick overview of our team. So we are at Forth. Forth consists of 10 institutes now. Computer science is one of them. You can see some of the others. We have biology, lasers and physics, astrophysics, of course, and so forth. So it's a big research institute, and within the computer science domain, there's a processing lab along with other labs. And we're fairly small and young compared to the other labs, like the ISL that Vasilis presented, but we're also trying to be active in research. So before starting the discussion, let me acknowledge people that support this work and actually people that pay the money. So a lot of this work has been paid by the Titan project. So it's an era share project that is led by Jean-Luc Stark from the Cosmostat lab at CEA, and is hosted at Forth, where the idea is how can we develop new models and new technologies for computational astrophysics, like astroinformatics. So let me get you to the main point of the talk. So, big data. I mean, I don't think I can argue in this audience about the proliferation of big data. This is just some numbers. You can see some plots about the amount of traffic that is generated. Most of this big data, though, typically is what's called the user-generated data. So it's like Instagram posts, Facebook, even YouTube, and so forth. At the same time, though, there is this explosion in big data happening in science. And astronomy and astrophysics as a special case. So these are some example of telescopes that are being designed and developed. So Vasilis just gave us a talk about the Vera Rubin or LSST. So there is an exponential growth in the amount of data that will be produced by these science institutes. And all this data now, instead of asking whether we have enough data, the question is, do we have enough algorithms to analyze this data? And obviously, I mean, nowadays we don't need to argue about the fact that AI is everywhere, and you can see ChatGPT. Like, if you want to demonstrate in the proliferation of AI nowadays, I mean, you plot the number of users in ChatGPT and the record that it made. But it's also making a huge impact in science, right? So AlphaFold, which is the machine learning system developed by DeepMind, a company that's part of Google, landed Demis Hassabis the Nobel Prize. And the reason for doing that is that this AI system was able to understand how proteins fall in space, and this was critical when making the vaccines for the COVID, right? So how do you actually fold the spike of the COVID virus in order to make a corresponding antibody techniques of fighting them, right? So AI has already benefited our lives in much more ways that we can, initially think about, besides the standard, funny, user-generated, amateur, ChatGPT type of problems. Right, and all this revolution, if you want to, identify what is the algorithm that actually made all this possible, it's deep learning. Right, so this is a technique known from the 70s or 80s, so most of the stuff that have been there for many years, but we're not really took up all these years for a number of reasons, mostly computational resources. So now we move from this era of neural networks that was in the 80s to what's called deep learning, pretty much the same mathematics, some tweaks here and there, of course, but pretty much the same idea, but super scaled. So instead of having small networks, now we have like networks with billions of parameters. And if you go into this direction, there are some phenomena that emerge. But besides this phenomena, the underlying mathematics is pretty much the same. It's the whole idea of propagating information by inner products and then using backpropagation in order to do what's called gradient descent to do through backpropagation. Right, so in terms of state of the art, I mean, I'm not going to go into detail. It's typically techniques that has to do with convolutional neural networks, where you exploit special information. And there is another big class of techniques that sort of focus on time. So this big class of methods focused on space, and this big class of methods focused on time. And when I say time, the thing that sort of makes time interesting is the whole idea of memory. So these systems have some notion of remembering stuff over time. And now lately there is this transformer architecture that sort of combines those two, so you can have what's called very long range dependence encoding. Right, so deep learning and all these techniques have obviously been applied in astronomy, right? So the easiest thing you can think about is taking an images and then analyzes these images from a space telescope in order to sort of infer some characteristics. And for example, in this case, the objective was to infer the type of galaxy, right? So is it a supernova, is it a variable star, is it moving, or whatever that is. Right, so pretty straightforward approach to that. I'm going to reiterate what Vasily said about the galaxy zoo. So how do you find label for this? And people actually, scientists, use citizen-based techniques in order to get through some process of selecting different characteristics and annotating, so providing ground truth data for the observations by asking many people and averaging the responses. Right, and nowadays the name of the case is multimodal foundational model, like Vasily was giving us. How do you combine information from multiple sources, potentially with text and with other types of modality, and getting them all together in order to answer your questions. Right, but I'm not going to focus on this because this is sort of straightforward. There are techniques out there how to do that. So I'm going to try to focus on the idea of uncertainty, and to that I'm going to give you a test, so hopefully you have your coffee if you're ready for that. So, get ready. Those are images of an Alaskan mammalute, right? And these are two images of a Siberian husky. So, raise your hands. Who thinks this is an Alaskan mammalute? Raise your hands, come on. How many of you think this is a Siberian husky? So you can see already that most of the people got it right, right? It's a Siberian husky, but not exactly. So for those of you that didn't find it, by myself, don't worry about it. This is called an epistemic uncertainty. People that found it probably realized that the build of the dog is a bit tougher from this one compared to this one, so it's most probably an Alaska and a Siberian husky. But if you're given enough examples, you would be able to yourself understand that, oh, look, this is the feature that distinguishes those two classes. So this uncertainty that was manifested right here, some people voted for one class, some people for the other, is what's called epistemic uncertainty. So this is something that information is there. If you're given enough examples, if I give you 10 more images of the specific breeds, you're going to be able to say that, I'm more confident about it. So this is something that we can address, right? So you can get more data, and when I say data, I mean training data for your biological neural network, and train yourself to reduce this uncertainty. Now let's go to another case. This is a cat. This is a dog. All clear? Right? So raise your hands. This is a dog. Here, how many? Dog, yes. What about here? Raise your hands. How many things to dog?
A dog.
It's a dog.
It's a dog.
It's a dog or a cat. Dog. It could be a dog.
It's a dog.
What about this? What about this?
It's a smaller dog.
So smaller dog. So how many dogs do you need in order to be able to understand that this is a cat or a dog?
6,000.
I can give you 1 million different dots, my good friend. You're not going to be able to say that it's a cat or a dog because it's just dots. Right, so the whole idea is that, this is a coin flip, right? I can give you 1 million of coin flips, but still a coin flip. I cannot learn how to predict a coin flip. So this is the uncertainty called aleatoric uncertainty. So this is part of the data that is irreducible. So the question is, how many examples do I need? Well, you can get 1 million of examples like this. It won't really help you besides going above chance. Right, so what does it have to do with science? So we're going to be talking about a specific case here in astrophysics called redshift estimation. So how did the universe start? If you see the Big Bang theory, it's fantastically portrayed. So it was a hot, dense state and then exploded. And then the universe started expanding over time. And what happens is that due to this expansion, observations tend to have a feature representation, what's called a spectrum, that it's shifted towards one side of the spectrum. This is called redshift. So information that is encoded, some spectral profiles that has to do with the galaxy or the object, as time moves along and the universe expands, gets shifted. So if you're able to reverse this process and understand how much shifting has happened, you can get an image of the history of the universe at whatever time point you want. And in doing those, in trying to achieve this goal, this is the reason we deploy so many telescopes. So JW Webb is fantastic because it can look in much redder regions, so you can see stuff that are much further back in the past and understand how the early times of the universe happened, right? So now the name of the game is, if you have observations like that, can you infer what is this redshift and understand how far away a specific galaxy is in order to get a 3D map of the universe? Well, you have two options. So option one is what's called photometry. So you have a telescope, you have a couple of three broadband filters, as they call it, and you image the observation. It's really quick, it's really cheap. You can do it with your backyard telescope. Well, in fact, it's something fancier, but still, I mean, it's relatively cheap. But unfortunately, you get only 4 numbers, so it's not that accurate. The other approach is what's called spectroscopy. So in this case, you have a very expensive machine. Instead of looking at 4 numbers, you get 1,000 numbers of the same information, and now this is much more expressive, much more rich. But it's also more expensive, right? Because you take time, and when I say expensive, it can be euros, dollars, but it's also like telescope time. So this is very expensive as a resource. So the question is, this is great, but this is expensive. This is not so good, but this is cheap. All right, so maybe I can use this data, and in addition to extracting information, maybe have some sense of how sure I am about this, so that I can potentially apply this technique in very specific cases. Right, so the nominal example I'm going to give you today involves situations where you actually measure 4 numbers. So these are the spectral responses in 4 channels from your telescope. You put these numbers in your neural network. So this is a very simple neural network. It's a multi-layer perceptron, the simplest neural network you can get. And you predict how far away this galaxy is. This is redshift. So from a machine learning point of view, this is called a regression problem. You're giving some input and you try to estimate, a specific number from a specific range. Right, so if you're to apply machine learning, the very first thing you could do is say, okay, I'm going to track a neural network, and I'm going to train my neural network. Fine. I'm trying to estimate a number, so this is a regression problem. I have an associated loss function, the mean square error. How far away is my prediction from my ground truth? I use my data. A fantastic thing that now we have a massive amount of open source data that we can use. And this is from the SDSS, this precursor of the LSST, and you can get your data, get 1 million examples, very cheap, very easy, and say, okay, so I have everything, let's train my neural network, and this is what you get. And you get plot like this. So in this plot, we have the true redshift that we know of, and this is the predicted redshift, but my system predicted. Now you may ask, how do I know the ground truth? Well, for these cases, I put aside the fact that I also have spectroscopy. But I don't give that information to my network. So I know that, but my network does. So I can estimate the true value for redshift, but my network does not know that. And then you get something like that, which is okay. I mean, from a regression point of view, most of the stuff are in the diagonal, so most of the times you're doing good. You have some outliers, some gross outliers, right? So this black hole is like millions of years or billions of years older than you predicted. But I mean, in general, it's fine. And from a machine learning point of view, if any one of you have tried training machine learning system, this is the loss function that you would like to see. The training and the validation loss keep going down. So this is great. But you see the problem, right? All of them are liquidly likely, but these are good predictions. These are bad predictions. How can I introduce this potential information into my system? Well, the easiest thing is, let's see if we can make our network now, instead of producing one value, produce something more interesting. For example, produce the mean value and the standard deviation. Right? So instead of predicting one value, say I'm going to predict one value, and then I'm going to predict a spread, given the Gaussian likelihood. So you do that, you'll modify your network, same architecture as before, but different loss function. Now you need what's called the negative log likelihood model this. You introduce those data, and this is what you get, right? Now, in addition to the dots, I have colors. And these colors now demonstrate how confident my system is in its prediction. And what you can see is that when I'm in the diagonal, when I make good prediction, it's mostly blue, so the system is sure. But whenever I get predictions that are far away, I'm starting to see yellow dots. So the system is telling you that, look, I'm making a prediction, but I'm not very confident in this prediction. So this is very useful, right? Because I can use this information and ask, okay, so what's happening with this sample here? So instead of randomly picking samples and saying, run spectroscopy those, I can only select the ones that are interesting, the anomalies, the strange phenomena, and only investigate those. And you get something which is good. However, you made an assumption that your distribution is a Gaussian. So Gaussian means it looks like this. When you actually go and you plot the residuals, you see that, well, it's not exactly Gaussian, right? So it's sort of sub-Gaussian. So it is a crude approximation, but it's not good enough. What else could you do? Well, Since I'm regressing, I can do what's called the quantile regression. So instead of predicting one value, predict the median and the median and the top and the lower quantile. So make sure that I have something that is bounded with a 75-25% boundary. And I can train my neural network. Again, I just replace my assumptions and my loss function. The neural network itself is the same. And I get things that look like that, right? Okay, so now we're getting something better. Now the color-coded scheme here corresponds to how big is the spread. So how sure are you between the 25 and the 75 percentile that you're actually confident? And you can see that you get something which is potentially a bit better than the previous case. So you can measure the interquantile range, and this numerical value is actually better than before. But still, I mean, it's not perfect in the sense that those are uncertainties, right? So the red, let's say, bars are uncertain, and there is a lot of uncertainty. So okay, I'm getting something, but how reliable is this thing? Is just my system splitting up uncertainty? It's like, yeah, it's like 3.5 plus or minus 100, and who cares, right? So tomorrow is going to be 25 degrees plus or minus 50 degrees. This is a useful prediction, right? So yes, okay, I get some uncertainty, but how useful is that? I wonder if there's a way of sort of calibrating this uncertainty. Good news, there is. Right, so there is this technique called conformal prediction, where the idea is that instead of actually having a system predict one value, for example, for the case of classification, say that this a fox squirrel, maybe produce a set of potential values that you're guaranteed to contain the correct one. So in this case, my system is not confident in what's looking. So instead of saying, you know what, this is a fox squirrel, it's going to also produce a couple of other options and make sure with guarantees that all the correct answer is somewhere within this group. Right, so even if I don't tell you one answer, I'm going to give you three answers, but for sure, one of these three answers is the correct one. Right, so this is the idea of conformal prediction. You can get similar ideas for regression, so you can ask how old is this individual. A point-like system will say it's 24. A conformal prediction survey, I'm 99% confident that his age is between 20 and 29. Right, so you get a region, but with guarantees. Right, so this is called conformal prediction, and the whole idea is you can take these quantiles and sort of recalibrate them to actually match the real observations and the real uncertainty you get in the data. Right, so I'm not going to go into detail. It's a modification of the quantile regression. So there are some tweaks and there are some techniques that you can introduce. But the whole idea is that you need to sort of recalibrate your regression so that these uncertainty regions actually up to something real. And we did test it, right? So this is the case of the previous one, so without any calibration, and this is the case for calibration. And what do we observe? Right, so you can see that this region here now becomes sort of more confident in the uncertainties that it has. So instead of having sort of blue or yellow, it starts having the different shades of uncertainty that sort of better capture this notion of how sure it is for any specific uncertainty. And you can actually get numbers to demonstrate that. So you can get what's called coverage. So make sure that 90% of the time when you give me a range, your value is within this range. And it's actually 0.9, which is exactly what you want. But unlike the previous case, the spread of this uncertainty is smaller. So this number says, how big is your uncertainty? So I'm having the same guarantees as before. So 90% or 99 or 99.99, so you can control yourself. I'm going to give the correct answer, but my quantiles are going to be very short. So I'm going to tell you tomorrow it's going to be 29 plus or minus 2 degrees, right? And it's going to be plus or minus 2 degrees with 90% confidence. So all these were techniques in order to understand how my neural network is actually doing the predictions. The question is, okay, but what about my data, right? So remember in the beginning that I told you that in some cases I have models, like the case of the dog, that we didn't know whether it was an Alaskan mammal. So if I had more information, I would be able to extract this piece of knowledge. But in other cases, like the very small images, I couldn't understand what's happening. So let's try to see whether there are techniques in order to capture that, the uncertainty that you have in your data, and sort of help you answer the question, how many data do I need? Right, so I'm going to tell you about two major ideas. So the one is called ensembles. So the idea of ensembles is instead of having one system, one neural network doing something, you have a lot of them. And each one is training a slightly different set of data. Right, so if I run all of these models at the same time, and then I average the statistics, and I see that most of them I agree that this is exactly the value. I'm pretty confident that my data really, the specific characteristic of my data really didn't affect my prediction because all my networks have the same idea of what's happening. If I start seeing variation, that means that some networks, so some data that are not represented, it's producing something that is sort of not consistent with the rest of the observations. Right, so I apply these techniques, and this is what's happened when you have a single model, and this is what's happened when you have multiple models. And what do you observe here? Right, so again, it's blue and yellow, fine, but there is this sort of distinct characteristic between this case here and this case here. And it is that those yellow spots here are now concentrated in this area, right? So most of my uncertainty now has to do with the fact that there is a region of my samples that I have a really limited amount of data. And some networks see a lot of examples in these regions, other networks see limited examples. So in this case, this demonstrates the situation where my system does not have access to enough data to be able to infer what's happening there, right? And if you don't want to run multiple neural networks, you can run a single neural network. And if you have any experience in systems like that, there is this technique called dropout. So if you allow this to drop out, effectively you have one network being run multiple times, and then you can sort of do the averages and the statistics, and you get information similar to that, right? So you see how now my uncertainty with the stuff that I'm not sure is there, but also the uncertainty with respect to my data is also manifested in my estimation. How do I know that there is uncertainty in my data? Well, this is the histogram of my data. In this region here, in this what's called low redshift, I have a lot of observations. Galaxies are close by, so it's easy for me to image them, whereas the further away I go back in the time and looking further away in the universe, I get much less information. Right, so this is manifested right here. Right, so we talked about techniques for capturing this uncertainty, we talked about techniques about capturing this uncertainty, what about this uncertainty? Right, so I'm gonna give you two sort of examples. And the first one is, in all the cases, you were assuming some distribution of some characteristics. What would happen if I would like to actually have the ground truth, right? So how do you get this ground truth? Well, I said that you get the ground truth of spectroscopy, but there is no instrument that gets observation and is a printout of the spectrum of the redshift, right? So you need to do analysis there as well. So this is a similar case, but now we're trying to find the ground truth. So we try to analyze spectroscopic data, and this is what happens as the universe progresses. These spectroscopic observations also change, and we apply the neural network, and we try to predict something that would look like that. So give me a galaxy, I'm going to tell you exactly one number, or a very small region of potential redshift numbers. And to do that, similar to before, we have a regression case, but now you say, you know what, if I actually split my potential ranges in bins, then I have a classification problem. And I know that machine learning is fantastic at classification because all of these data sets and all of these fancy techniques are based on this classification. So I wonder if classification will do. So I sort of need to modify the network for some specific reasons. Excuse me. And you get information like that. So this is what happens with regression now, predicting one value. And this is what happens if, instead of predicting one value, you actually predict a full distribution. And you actually plot the information from this maximum of this distribution. So in this case, what you see is that if I reformulate my same problem, but now as a classification, I can get much better performance and also distribution that I wasn't able to get before. Right, and for my last sort of theme, I'm going to switch gears a bit, and I'm going to tell you about another problem. We're still in the case of uncertainty, but now the question is what happens with the uncertainty in the ground truth? How do you know that you are actually saying this is a redshift or this is a phenomenon that has a value 3, that is actually the correct number? Right, so this is another problem in astrophysics called as gravitational lensing. So the idea is that light starts from a galaxy, and as it moves forward, because of gravity, space-time, according to Einstein theory, space-time bends, and this bending causes light to distort, similar to what it would if you go through a lens. And this is called gravitational lensing, and you can get beautiful information like this, which is called an Einstein ring. So what happens here is that you have a star in the front, and then in the back there is a galaxy in the beginning of the universe, and its light is diffracted like this. So the question is, if I have the diffracted light, I wonder if I can sort of estimate what happens behind the star. So this is a universe scale telescope. So this is much bigger than anything that we can potentially build because we're using stars to magnify things. And you can have also this called Einstein cross. So I'm not going to go into details because it's astrophysics, so it might be not that relevant. But what's interesting here is that in our system, which is a simulation, and trust me, astrophysicists love their simulation, our system, instead of assuming that for every observation I have some numbers, I gave it a range of numbers. So this image here, which is called the gravitational potential, is characterized by two numbers, like alpha and beta. But instead of saying the neural network, well, this is alpha and this is beta, I say, you know what, alpha is between here and there, and beta is between here and there. So I'm not sure about my label. It's not like before I was saying, you know what, this galaxy has redshift 4. Now it's like I have no idea. But given my assumptions, my model, I think it's within this range. What can the network do? And to our surprise, once you introduce a network like this, with ground truth, with target variables looking like that, the system did not produce this. It produced this. So it produced something that was actually far more accurate than what it was trained on. Right? So even though we trained the system with values in a big range, the system was able to sort of shorten these states and identify that, you know what, this most likely value for alpha is 0.3 instead of giving you a range. And we're able to do that, again, by modifying the optimization. So if I would like to say the take-home message that the mathematics at the end of the neural network is a different story compared to what's happening with all these big networks and the transformers and so forth, right? So feel free to use whatever big companies make, but the mathematics at the end is the thing that's going to give you the power to understand the context of the problem. Right, so this is just a visualization. So effectively, as I said, we're giving ranges like that, but instead of producing ranges, it actually produces sort of Gaussian things. And it was actually shown that to be more accurate. So I'm going to try to wrap up this discussion with some take-home messages from an investigation in this topic. Right? For example, I gave you some examples of uncertainty. Those are big groups. But if you are versed in this topic, you could argue that, oh, look, wait, there are Bayesian neural networks, there are other techniques for ordinary regression. But the most important thing is there is some uncertainty that has to do with your model and some uncertainty that has to do with your data. The uncertainty that has to do with your model is something you can work on. You can get more data, you can get a better machine learning, you can fix that. But there is a point after which there is no reason for you to collect more data. There is no point for you to get a better network. You reach the plateau, this is the uncertainty of your data, stop there. This is the best you can do unless you have access to other data. Uncertainty is something that is not really investigated, mostly because the community is working on classifying cats and dogs, but science works on that. So if you're doing scientific analysis, people are going to say, I detected gravitational wave 4 sigma, so this sigma is the uncertainty. You're not going to find in any cats and dogs classification, for sure. Time, I didn't touch upon time. Time is fantastic, because for a machine learning point of view, time is great because you can always forecast what's going to happen tomorrow, and then tomorrow you have the absolute ground truth. But there's also the uncertainty, right? So how much of this is deterministic and how much there is chaotic component in your stuff that change over time? Space, so this is more technical, I'm not going to go into details, but it has to do with the spatial characteristic of observation. And then, if you're going to say, okay, so what is the next frontier? Multimodality, at least for the case of astronomy and astrophysics, right? So integrating observations from multiple instruments, using the techniques that Vasily showed you before, and actually, developing machine learning models to analyze those data. And before I thank you, let me just, sort of advertise our workshop that's going to happen in Crete. So if you're looking for a second excuse to visit Crete, there it is. It's middle end of September, fantastic weather. At 4, fantastic location. On machine learning for events, imaging systems, observation analysis, and sensing. Fantastic topic. So if you are interested, this is the QR. Look, go in, register yourself, and have another excuse to visit Crete and listen to some science as well. So thank you very much.
It's beautiful, thank you. Okay, so we have time for 2 or 3 questions. Questions, thoughts, remarks, doubts, curiosities, perplexities? Of course, I have a couple. Right on.
Hi. So thanks for the presentation, really great. I read that now there are people experimenting with trying to imbue in some of these neural network architectures some of these physics-inspired principles to try to take things like how gravity interacts with stuff and how these can interact towards classifications. So have you meddled with some of those types of neural networks, or how do you consider the potential of that?
So that's a fantastic comment. Thank you very much for pointing this out. You know, this whole idea of physics to inform neural network, and the whole idea is that we have some physical models of things, how they work, and this should be infused. Indeed, it's a very active domain. There is no clear-cut approach in how to do that. There are a couple of good candidates, and each of them has different characteristics depending on what is your physical model, but for sure integrating those. And in fact, in my view, this is the next thing for the generic machine learning, right? So now we have, general purpose machine learning. I don't know if we're going to reach the, the advanced, intelligence or whatever, but for sure we're going to verticalize first. So for sure we're going to have systems that are, focused and explicitly on different domains. And for example, if you're trying to do something with astrophysics, well, physics should be there. So for sure, this is an important thing. Also for climate modeling, that this is another domain that I work on. It's also becoming very, very relevant. Explainability as well gives rise to that. So this is an excellent question, for sure.
Okay, thanks a lot. Further questions? We have time for one more question. Okay, maybe I can pose my question. So I'm an operations guy, so how much would this cost operationally? So if I have my pipeline, which doesn't have any uncertainty tracking or any quality assessment or metrics for that, how much would it cost for me to change my pipeline to accommodate this?
If you can parallelize your pipeline, assuming you can do that, then you can do what's happening in numerical models, which is another domain, which you run what's called ensemble. So you run the same system multiple times. And then the overhead is like how many times you run it, of course. You need some post-processing, but it's not much. So effectively, it could be something as easy as like that. Now, in principle, you would like to introduce some modification to your system to actually produce that or report that. And why? For example, why would I care? Because you can get an alert of something that interesting happening. So maybe your operational system needs to trigger some alert mechanism. So it's typically, in extreme event situations or anomalies that you have a threat like that. So, I mean, if the value that you get out of running this system multiple times is worth the effort, that's fine. Otherwise, I mean, you can, of course, you can take, trade-offs, right? So how many models do I need? And, in my experience, like 3 or 4 models are fine to give you an estimate. Of course, you can do 100, but that's like waste of resources. But this is actually a key research question. How many models do you need? Because those cost money, right? So you can run travel indefinitely.
Yeah, I agree. Okay, further questions? Otherwise, let's thank our speaker again. And that leaves us to lunch, I suppose. Yay, lunch. And then I think for the tour, we're going to meet outside the front door in 1 hour, Frank. 1 hour?
Yes.
And 5 minutes. 4 minutes. Okay? Okay, see you later.
Why?